Okay, hello guys. Today it's our 10th numbers and names. Okay, where is this thing? Huh? Interesting. I lost somewhere. Okay. Any questions on previous?
No.
You have no questions, guys?
We do.
Okay.
How do you get a frame of reference?
What is what? Frame of reference?
How do you come up with stuff like that?
One of the questions was, what can be a frame of reference?
Yeah, in logic, right? What is the frame of reference in logic? So did you answer this question? What do you think?
No.
Huh?
No.
Okay, I give you a clue because I want you to think a little more about it. We can speak about it later, but a clue for this. Just think. Remember we were talking like this particular person, right? What's the name of that person? Who was a human?
Plato.
Huh?
Socrates.
Socrates, right? Socrates, particular person, right? So look at this. Like we have frame of reference like in regular mathematics, x, y, right? And there is, like for a vector, we talk about vectors, right? So there's a point which have coordinates, right? The starting point and the ending point, like A and B, right? Now, we have this particular value of like x coordinate of the beginning and the end of the vector, right? If you change the frame of reference, so for example, you move it like to the right, right? Like for example, you have like this frame of reference. The vector is invariant, so vector is not changing anywhere. We're changing our frame of reference, right? This is y prime and x prime, right? You see that coordinates change. Like for point A, it becomes even negative, right? For point B, it becomes negative 2 here. You see? The coordinates change. What it means? The points are the same. But when we change the frame, actually it looks like that the points has been changed. So what it means? What do you think? Like if we're talking about Socrates, this is the beginning point, is human, right? Remember?
Yeah, we were just doing that.
So we shifted for one change of reference. We shifted frame of reference. What will happen with this Socrates?
That means Socrates is human. That means he's a human being.
Socrates is human. Socrates is human, right? So they may be the same by themselves, right? But what will happen? This is if you think a little, the coordinate of the point is a name of this, like A or B. So we will have the coordinates. It was x in one frame of reference. It was x prime in the other frame of reference, right? So what changed for this point? The name. The name.
Oh.
So here, yeah. So here we'll get somebody probably with different name. So and you think further about it. What about human? Because human will be changed too probably. So what will happen with this? And what will happen with this? The third point in this syllogism, right? The third point is mortal, right? So it's a feature of human. So it should be changed too. So just think about it. But this I think this is.
So like, can you say it like this? From the point of view of philosophers, Socrates is an accomplished person, or something. From a point of view of a reference of I don't know, a pagan Satanist.
Okay.
Socrates is a really bad guy.
Okay. Yeah.
But
it's the name change too. You know, from the other point of view, maybe he's not Socrates at all. Maybe, as you say, maybe his name is bad guy or whatever. right?
Bad guy.
Yeah. Or maybe good guy. Or it's not a moral value, but it's about like just a name, right? So the guy came, an alien, whatever. So just think about it a little more because it's good to think about these things, but you got a clue, right? Okay. So today we will talk about something that we a little touched before. The first is groups, and you never heard about this probably, and algebras.
Oh yes, we have algebra books actually. Well,
You have algebra books, yes, but algebra is a much more general definition than just algebra to have in your book. So we talk about symmetries, right? And we talk about that the symmetries actually, the operators. Remember these operators of symmetry. So transformations, which transform one object into another, right? These operators, they actually form what is called groups. And now we'll talk about this a little more particular, a little more in details. So what is a group? Group, you can see here, right? Group is a set of elements, so operators, transformations, whatever, some elements, set of elements, which has an element, certain particular element, which is called unit. So with unit of the group. And defined operation. Not only operator, but operation. Operation means the certain way of combinations, elements of group, combination. So you took two of them and combined into something else. An operation should obey that rule. If A is an element of this set, so some element of the group, some operator, and B is element, again, an operator of the same group, so this combination AB, which is often used, which often said that it is like operation of the group, or sometimes they call it multiplication and put this sign here. But wait, it's not. It was used multiplication, but just be accurate, very accurate, because it's not multiplication that you know. It's just a word that is used. So remember that it's a group operation.
Just call it.
Yeah, they just call it multiplication because it's written like multiplication. You know, like multiplication usually is written like AB, right?
Yeah.
So and when you do it like this, combine two elements into this pair, it equals C, and C must belong to the same set. It is called this set. In other words, it's called closed set.
That is true.
Closed. So A and B are elements of the set. So A and B paired, so combined by this operation, equals to C, which is an element of the group. So the group is like whatever you do between elements, we still stay in the same group. And of course, like I said, the main examples of such operations, such groups, are groups of symmetry transformations. So the first will start from certain thing, which is called, remember this symmetry, which is called rotation.
Yeah.
Rotation. Rotation means that you have some radius or vector, right? Radius. And you rotate it usually counterclockwise. This is called plus direction. In mathematics, usually this counterclockwise, it's used as plus rotation. And in this rotation, it's called minus. And we have, of course, this point, right? It goes like on this circle, right? If you rotate it like this, it goes in this circle. And I think I told you, but just to remind, that the angle that the angle, like alpha angle, alpha is a Greek letter, so alpha, the angle is defined like this: the length of this curve up to here, L, divided by radius. So the longer L, like we rotate, L is growing, the R is the same, right? And so we have this. And I don't remember did I tell or not, but we can find it again. Do you think, and this is the measure of the angle measure. What do you think is alpha for the whole circle if you make rotation on 360 degrees?
I would say it's 30 degrees.
No, 360 degrees, like it's the whole circle, right? We're rotating, and to come to the same point, right?
Yeah.
So what do you think this alpha will be?
30 degrees.
Why do you think so?
Because it looks a third of the quarter.
No, it looks like, but it's just a picture. It can be this way or this way. The R can be this way, you know? Like one of the positions is here, then here, and then it goes to the whole circle.
Well, yeah.
For the whole circle, which is L for the whole circle? What do you think? If you make the whole circle, what is the length of this curve?
They don't really know.
They don't know? Okay.
They don't know the formula.
Okay, so the formula, okay, I thought that you remember. Okay, the whole circle is the whole, LH.
They don't know the number pi. They don't know it.
Okay, it's 2 pi, remember this pi number? Pi is like 3.14 and many other digits, but it's mainly 3.14. 2p radius.
Pi.
This is for the whole 2 pi, sorry, yes, 2 pi, because in Russian it's pi. So 2 pi radius, right? 2 pi. This is the whole thing. And this measure is called radian. Radian. So in the whole circle, or 360 degrees, with this measure, it will be 2 pi and divided by r, right? So the whole...
R divided by r equals what?
2 pi r divided by r equals 2 pi.
That's
2
right.
pi r divided by 2 pi.
Did that?
Oh.
Did that? 2 pi r divided by r equals 2 pi.
2 pi r divided by r equal to 2 pi, yes. It's 2 pi, so it's the whole 360 degrees. That's the same as 2 pi radians. That's how they usually measure this in mathematics and in physics. In radians, not degrees. Just for you to remember something like a good thing. Now we talk about this and these rotations a little more. Okay? Remember, we talk about this unit of the group. What is this unit of the group? Definition of unit of the group is, it is usually noted like E with the index 0. So this is the unit of the group. And definition is, if you have some element of the group and you combine it with this unit, this will not change the element of the group.
So then E would be 0.
No, it's A.
If E was 0, everything would go 0 then.
And the same thing is if you do it like this. A combined with E0 like this. So you exchange the positions, it will still be A.
Times E to the power of 1.
So this is the definition of unit of the group. So unit of the group, when combined with any other elements, it does not change the element at all. So it's something that does not do anything. But still, it's very much needed. You will see it a little later.
Really?
So the unit, yes, unit, remember, definition of the group. Group should contain the unit. It should contain all the groups of elements, right? A, B equals C, it's closed. And there should be unit, like this. So this is a very important definition of the unit of the group. And let's look at these rotations. Like we're talking about rotations like this, right? What do you think can be a unit of this group? So we have the transformations or operators which are called rotations. Rotations at certain angles, whatever angles are. What do you think could be a unit of this group? Something that does not change anything.
How far do you have to turn so that you're in the same place?
360.
360, right, exactly. Or
one full turn.
what about 0?
Yeah, what if you don't turn at all?
Oh yeah, that's true.
0 degrees equals to 360 degrees in this case of the group, right? It's the turn to 0 degrees is the same at 360. Any more? What do you think?
If you turn 2 times?
Yeah,
You're getting close.
Papa, there's an infinite amount.
Yeah, right. Throw 360 plus.
What?
So what kind of degrees would it be?
0.
No.
0, then 360, then
120 degrees.
But loud, speak up, speak up.
Did a 720 degrees.
720, right. Something more?
Oh, wait, 1,080.
Yeah.
1,080 degrees. There's also 1,440.
1,080, Katya said.
1,442.
Okay.
So, what if you turn around X times?
Okay, 720, it's okay, right? You calculate this correctly, right? Plus 360, right? How much would it be?
That's 10,080. Katya said that.
Okay, great, great. So Katya is right. So and then you can add whatever you want, right? This is in degrees. And what about the radians, rads? What it be? 0 degrees, 360, 2 pi, right? Or 0 rad, or 2 pi, or how many pi for the whole thing? 2 times.
For X times, how many pies is there?
X. I don't understand X pi.
No, a single turn is what? How many pies?
The single is
2 pi.
2 pi is single term.
So 2 turns is
4 pi.
4 pi.
X turns is
X pi.
6 pi.
2 pi times X.
And,
Yeah, 2x pi.
and whatever. But you got the idea, right? You got the idea. And now let's go a little further. Okay, we have this. Now let's talk about the simplest group ever. The group that is a set of just one unit. This is a unit of the group, E0. And with these brackets we will denote the set, right? So the elements of the set. Just one element, E0.
No, just assign it to the group.
So this is the group. That's very simple. Sometimes called degenerated group because it's nothing except one element. E0. Let's talk about this E0. Okay, with the index 0. It's E0 grouped with E0 or multiplied by E0. What would it be?
0 squared.
Eh?
Oh yeah, that is 0 squared.
Okay, E0 squared, right. And remember this definition of E0? E0 multiplied by any other element is
0. 1. 0. Oh yeah, 0, 0, 0, 0. Oh, they're the same.
huh?
Right? 0.
0? Do we have 0 here?
Is it a 0?
This
What
is a set. Remember, there's only from here this set. There's only one element in this set. We should not go out of this set.
No 0 in there.
There's no 0 in this
What's
set.
the
I'm
set?
sorry. There's unit E with the index 0. Yeah, that's all. That's all. This is just a notation, just a name.
So you cannot get anything but E. So what is it then?
E.
Very good.
Do we have E here?
Yeah.
Well, it's E0.
Yeah, we have only E0, right? This is the name. Like I'm sorry if it's Kate. It's just Kate, not K, right? It's not a person K from Men in Black, right? So she's a real Kate, right? So Katya. So we have E0, the whole name, E0, the name of the element, E0. We cannot find anything in this group except this one element. Okay,
Yeah.
so remember definition of a group, okay? I will tell you again. Definition of unit. This is a rule for the unit, group unit. So looking here, what would we see? E0 multiplied by Z0, what would it be?
E0.
Yeah,
Oh, that means that.
like here.
Oh wait, E0 means E0 is 1. E0
Yeah,
is 1.
E0 here, it's like A here, right?
It's not 1. It's a unit.
It's a unit. It looks like 1. Yes, 1 actually plays some role in the other group, which is called a group of multiplication of the numbers multiplication. What you know in the algebra, regular algebra, the numbers algebra. But here we're talking about abstract groups. So just these transformations or operations, operators of certain symmetry, whatever it is. Right now we're talking about rotation. So probably we can talk about group of some rotations here. So you got this? You got this?
Yep.
So this all very significant. So E0 multiplied by E0, E0 squared, it's written like this. Yes, it's correct notation, and equals to E0. So this is because E0 is a unit. And what do you think, this group, what it corresponds to, what it actually shows you, what it says about what kind of rotation can this be? What do you think?
360.
Yeah, exactly. Or 0, right, degrees. Or 720. So any of these rotations are they call it represented. So it's called representation. Represented, the group rotations by 0 degrees, 360, and everything, and like this is represented by this particular group of one element. Now let's take a look a little further. So we have here like 0 degrees, right? Rotation. Now we talk about the angle which is called the right angle. How many degrees is it?
90 degrees.
90 degrees, right. So 90 degrees means like this, right? And can you guess how many pi's are here? How many rads are here? With this angle.
Wait, that's 360 divided by 4.
Okay.
360 divided by 4 into 2 pi's. Oh, that would be like 0.5 pi.
Don't
Did it! It would be 0.5 pi.
Yeah. P, it's a half of P, right? And
because Katya doesn't understand why it's pi over 2. You gotta ask questions, Katya.
Yeah,
I
sure.
don't know why it's pi over 2.
the whole thing is how much? The whole thing.
360.
Huh?
In pies, in
In
red.
pi's, in red.
2 pi.
2 pi's, right? 2 pi's, yes, right. But this is just a quarter of it, right?
Yeah.
So 2 pi's divided by
What pi?
Oh.
2 pi's divided by 4, right? 2 pi's divided by 4 equals
When was the last time we did math?
P over 2. That's okay. No problem. Just because it's a rads, a little confused. This rads, p's, pi's, and everything, right? So, and then let's talk about this kind of operator or transformation, right? It turns our radius vector from this position to this position, and the angle is p over 2, right? So, or 90 degrees, right?
I thought that was pi.
Let's okay. So we have in this group. And we are looking about these kind of rotation. So what we have here, this was the first group, right? Now we're talking about the second group. We have, of course, some unit element. It should be in any group. Unit element is still here, right? It's 0 degrees. We still have it here. Then we have this term p over 2, right? We call this e1 with the index 1.
Mhm.
Okay.
Yeah.
Now we can try to do something like if we have e1, right? We can multiply it by itself, right? We know that e0 multiplied by itself, it will be still e0, right? E0 multiplied by E1 or grouped, it will be what? E0, E1, whatever E1 is. E1 is here, the term for...
Oh wait, it would still be E1.
E1, sure. So we know this, right? Now about E1's by E1, what is this? It's E1 squared, of course, right? Like here. We can write it like this, right? And what would it be here? If you look... It's the first is P2, right? Turn to P2, turn on right angle, and then another P2. It's continuation. So we have here. It's another P2.
180.
Yeah, it's 180. Or
One pi.
1 pi, right? So it's 1 pi. Yeah. It's 1 pi or 180. Yes, you're correct.
Yeah, I see it.
Now, okay, so if we try to do it a little more, E1 by E1 by E1, it will be E1 tripled, right? So on the power of 3, right?
And the quarter pi.
And?
Yeah, the 1 1/4 pi.
Yep, exactly. So 3/4, right? 3p.
That's one.
Do the 1 1/2 pi.
Oh, sorry, three twos. 3 twos,
Yeah.
right? So,
That you listen to Visa.
yeah.
You shouldn't have listened to Visa.
Yeah. Okay. Okay, so, okay, this one. And what do we have else? If we try the 4th, right? So we try again, right? It will be e to the power of 4, right?
1/2 pi.
Yeah.
And
That equals 2 pi.
it will be 2 pi. And what element is it? What do you think?
E1 to the power of 4.
Right, but which
Yeah.
one is it?
What do you mean which one?
What is this? What do you think?
Circle.
What
360.
Which is?
What element of group is it?
E0.
E0.
Well,
Exactly. So you see, with this interesting turn, with this symmetry, we are talking about turning to the right angle, right? We have how many elements? We have E1, right? Then E1 squared and E1 to the power of 3, because E1 to the power of 4 is against the same thing. So we have group of 4 elements. Just 4 elements. Is it correct or not? What do you think? Do we have some other turns here? Like for example, if we talk about turn not this direction, but this direction. What do you think? Like this. Yeah. Okay. What's the question?
That means E1 equals 1/4 of E0.
A quarter of E0. Yeah, that's a great idea, but unfortunately we cannot divide this element by the numbers. They are not numbers. Remember, they are operators of symmetry, transformations, very generic.
Wait, Dita, is
We
there
cannot
8
divide.
elements?
Hmm?
There will be 8 elements then, right?
Yeah. Okay.
Because it snaps away.
No, just look at this. Okay, let's try one thing. We know this turn, like, and that turn, the whole thing, right? Right.
Yeah.
Right. Let's try this minus direction. Let's go not this way, not counterclockwise, but clockwise here. So from here we go to this position, right?
Minus E1. Dita, minus E1. Minus E1?
Minus E1. Okay, that's a sort of a good idea, by the way, because you think that minus is actually, I'm sorry, minus is actually the opposite to E1, right? Yeah, this is plus, this is minus. But unfortunately, remember that we're talking about group combining, right? This operation of between the elements, right? We talk about multiplication. So it looks like it's not multiplication, but it's written like multiplication. And because it's written like multiplication, the definition of this opposite element actually is written like this. So opposite element, or it's called inverse element, right? Element inverse to E1 is E1 to the power of -1.
What's that first thing? E1 to the power of -1.
Inverse to this.
1 over E1, right?
And now we come to some other definition, which is very useful for the groups. The definition of inverse element. Inverse or opposite element is defined by this. If you have two elements A and B, right, which gives you unit A-B unit, then it means that B is opposite to A. Opposite or inverse. The real term is inverse. And they write A by A minus 1 equals this.
Oh yeah.
This is the definition of opposite element. Do you know, by the way, the powers of -1? Have you ever?
I know how to do
You know,
that.
it's like in regular, it's 1 divided by, right?
Yeah, like 1 over 8.
So should be familiar with this at least. For multiplication, it's very useful, so easy to remember, right? But remember that they are not numbers; they are all operators and transformation of symmetry, whatever.
Divided by 1 half.
Yeah.
Oh.
Very good.
Oh, so it's 1 over 8, okay.
So this because we defined this term like E1, right? This is E1, right? This is definitely E1 minus to the power of -1.
Yeah.
So the first idea of Vitya was good, just the definition, the notation is different. That's all. So this is E minus 1. And what do you think this can be, if you think about it? There's a little. Look at these things.
How to get there?
Yeah, how to get here? Can we get here from these elements that we already got?
Which way? Tell Zeta.
Turn the opposite way. To the opposite side.
No, but
One.
you can only turn counterclockwise.
Clockwise.
No. You can only go one way.
No, we can, but we just want to understand what is it, right? Does it really belong, does this transformation belong to the group or not? We have only 4 elements here. Huh?
You could do E1 tripled.
Yeah, exactly. And we know what is this, right? E1 tripled is this, right?
Oh yeah.
E1 to the power of 3, remember? So we can say, looking at this rotation, that
E to the power -1 equals cubed.
Yeah.
E1 minus is E3.
In this group, right?
In this group, in this group, yes, exactly. In this group.
This wouldn't be true.
Exactly. Yeah.
Only in this group.
Yeah.
And now the same thing we can talk about this position. Like if you go this or this, right? It will be E squared equals to, what do you think? This is E squared, right? This is E to the power of 3. This is E squared.
It
E1 squared.
equals to E to the power of -2.
Minus 2, right? Minus.
Oh, that's 2.
So,
Yes.
so just play with it to understand how it goes, okay, guys? Any questions to this? I think you understood, right? Okay, so now just a small thing. Now we may talk about, just very short, about terms like to 1 degree. Like let's example that the angle is just 1 degree.
Yeah.
How many elements do you think would be in this group?
I think 360.
Huh? Yeah, right. So for this, if we use this operator, E0 should be always there. It's a unit, right? And E1 It's just for 1 degree, right? One degree operator, right? So
Yeah.
there are many, and this will be the power of
Power of.
it's 360 degrees, right? And the last element would be the power of what? 300?
360. How many is that?
360?
Minus 1.
No, let's try it. 360 will come exactly to that position, and this is E0, right?
Yeah.
So it will be 300.
60 minus 1.
360 minus 1. No,
359, guys.
Oh, that's like
Yeah, just minus 1.
I thought you meant.
So we have 360 elements in this group. 351 to this and E0. So this group, by the way, this group, you see, they are they all are just some powers of the first element, E1. This kind of element is called generator of the group. The number of the elements called the order of the group, right? And the whole group like this, which has only one generator and finite amount of elements, is called cyclic.
It's called segment?
Cycle.
Oh, cyclic.
It's easy to see because we're talking about rotation, right? In circles, right?
Cyclic.
It's cyclic group.
Oh, cyclic, not cyclic.
Cyclic.
It's a cyclic group.
Okay, cyclic, whatever you. Cyclic or cyclic?
Cyclic.
But bicycle, okay, cyclic, okay, whatever.
Bicycle.
Bicycle, right.
Sickle.
But
It's a
still,
cyclic group.
is it a cycle or a sickle?
Oh my god, it's a cyclic group.
No, really.
Pickle. It's a picklick group.
Okay, cyclic, okay, whatever.
It's a cyclic group, it's got a generator.
Okay, generate, okay. Okay, guys, and now just small example, and we'll finish with this. Okay,
It is interesting.
the first is definition. What is algebra? Algebra is the same like set of some elements, right? Again, closed set. Where defined two units, two group units, and two operations. Like for example, like operations addition and multiplication. Two operations, for example.
Yeah.
That's if we have the numbers, right, regular numbers, we have this algebra where we have first addition and of course subtraction, like opposing, right, because like 1 minus 1, it is the same as 1 plus minus 1, and minus 1 is inverse to this.
1 plus minus 1 is 0.
And the operation is plus here, and it gives 0. So 0 is the first unit. It's first unit. And guess the second unit of the algebra is? What do you think?
1?
The second operation is multiplication. The first is addition. The second is multiplication.
So 1
Right?
times 1 equals 1.
So for multiplication, okay, we have this, right? Definition of the unit, right? Multiplication. So if this A and these are numbers, what do you think is 0 is? You named this before in the beginning.
360?
No.
1.
Multiplication. Just numbers multiplied.
Oh yeah.
What's it?
1.
1, right? 1. Exactly. So 1 is second unit. And both two operations, plus and multiplication, of course, minus and division, right? And two units, 0 and 1. And when they combine together and the set is closed, so you never, whatever you do, plus, minus, multiply, divided, you never go out of this group. And the group is infinite in this case, of course. If you're talking about numbers,
Just remind
like 0, 1, whatever, it's infinite group.
0, 0, 1,
So there are finite groups that we talk about rotations and infinite groups. And actually even continuous groups when we talk about numbers like pi or whatever. Rational numbers and irrational. Yes, I'm listening.
When are we going to learn binary?
Binary, what binary?
Like, you know, like, one time at the beginning, I thought you said you were going to say something about teaching us binary.
What about binary? Binary just a way of how you represent numbers, right? You can represent the same number, like 3, can be represented in many ways. It may be binary, like how is it called? Ternary? Forgot. What is the term? Huh?
Decimal.
Decimal or hexadecimal, like lots of different bases for the number format. Okay. So you got the idea of algebra, right? And now some interesting example of algebra. The first, you know, right? The main, very well known to you, it is the algebra of the regular numbers. And now we'll talk about some interesting algebra, and we'll talk about time. This is time. So we have time, right? You can imagine what time is, right? And we have like past time.
Yep.
Past. And past goes to present time.
And present time goes to future.
And present time goes to future.
Future. And then future goes
and
back
we have this. And we have this sort of triangle, like there are vectors. Remember? See, they're oriented, right? Past, present. There are objects. Between them, there is a direction from past to present. Time goes only from past to present, and to the future, right? So we have some sort of triangle. We can close this triangle by this, and this is the vector which says past to the future directly, right? Now some
I know how.
Some smart guy, forgot his first name, was in the 19th century. His last name was Hamilton. Hamilton, yeah. He invented for something, the idea is something like this certain notations. Like he said that one vector we can call I, second vector we can call J.
Vectors?
Yeah, vectors, right? And sort of. And this vector called K. And if you take a look at them as a group, you may think about something like this. Like you see these vectors, right? A and G. Remember this about symmetry operations. One operator, then another operator. It gives you this operator, right? So we have AG equals K. We can write it, and if we define, again, this is all about notations. If we define the opposite or inverse, like minus, like you suggest, Vita. So we have this, like I plus I. This is the first thing. Here is multiplication. Here is like plus, but again, there is very not that similar to your plus and minus, but very close to the numbers plus and multiplication. I plus I, it's 2I, like normal. So if you adding, you have this I, and this is vector which is 2I, right? This and this. And this is like addition. But if you do like this, if you do I minus I, so it means that you add this vector to that vector, right? Minus I is opposite. Will be what? Will be 0, right?
I can't really see from here. 0.
Get closer.
So Hamilton was pretty tricky and smart guy, and he said, okay, this is like inverse. So inverse to this element I. So inverse is, remember, it's -1, right? He said that it's the same as -I. No, just he defined it like this. He said, okay, inverse element to I is -I. It means, and if you write it like in regular group, right, -1, it is, oh, sorry, minus I to minus I, and you can say, what is this? It's minus I squared, right?
Oh yeah, minus I squared. It is the same thing times except it's opposite.
And also, by definition of a group, it should be equal to I to...
I squared. I mean, it's,
Oh, this multiplication, and the unit of multiplication is, remember? Unit, the unit of the group. It is 1.
Okay, -1 squared. That's 1.
Well, no.
So it means that...
-1, yes, but if you just adding minus to the square, it's not.
Yeah.
It means that I squared equals -1.
Meaning I equals the square root.
Look, read that. I squared equals -1. What number squared gives you -1?
So it is not a number, but it's called virtual number. I think virtual, imaginary number, right? So
Imaginary.
imaginary number, yes. Imaginary. It is called like this, but it's not imaginary, of course, but it's called imaginary number, and it's squared that equals to -1. It's a very interesting number.
That means I equals the square root of -1.
Say it again?
That means I equals the square root of -1.
Oh, I didn't get it. I'm sorry. What say again?
That means I is the square root of -1.
Can you say it slowly? Because
That means I is the square root of -1.
oh yeah, right. Yeah, you're right. But it's not exactly like this. It is like this: minus or plus square root of -1. Because minus square root and plus square root give the same -1. You understand it, right?
We've never done that.
So it may be minus or plus. It's not like strongly defined in here. This is the strong definition. I squared is equals -1. And now if you look at all this, it seems maybe okay, but a little weird, right? Let's try to do something like this. Let's change both vectors, this and this, to opposite. So it will be -I, right, like this, right? It will be -j, right? And according to the same logic, this vector will be, you know, combination of these two, it will be -k, right? Because -k is here, so triangle, just opposite triangle to this. And you may write it like this. So j minus j. Where? Okay. I'll write it probably from here. Okay.
All the variables there are minus. I'm negative.
Yeah, both. Here's minus I, and minus j. So vector here and here. And according to this triangle, should be minus k. Just looking here. Right. So let's write it like so. It's minus j. Goes first. Then it combined with minus I, right? And it gives you minus k. Minus it's plus, so it's ji, right? Equals minus k.
Okay.
Take a look.
That means that a k was negative to begin with, right?
Now take a look. A by j equals k, but j by I equals minus k.
J times I equals minus k, but I times j equals
So
k.
if you you see you change the positions, change the order of these two. A by j is k, but j by I is minus k, and this works this way. It's called non-commutative. So
Yeah.
it is non-commutative algebra.
Yeah.
It's not what?
Non-commutative. So commutation or commutate.
Commutative.
Yeah, when you exchange the numbers, it's called commutation. So it's called non-commutative algebra. So when you see, just look at this triangle. It shows you how it works, right? So it's very interesting thing. So you just have to understand that some groups and some algebras are non-commutative. So just it means that if like in regular algebra, 2 by 3 is 6 and 3 by 2 is 6 either, right?
Yeah.
It is not correct in non-commutative algebra. So the regular algebra, the number algebra is commutative. But not all algebras are like this. Not all algebras. Any questions to this? Yeah, maybe you know some interesting thing just for you to remember. First of all, that this is called quaternion algebra. Quaternion algebra, and the main thing here, the main rule is like this. So like 3 vectors. So if you want to remember how to operate them, E by G is K, K by E is J, J by K is I. If you go opposite, it's quite opposite. J by I is minus K, and all the rest. K by G is minus I, and something like this. Your papa remember this, so you can ask him on this.
I did the report on quaternions in high school.
So it is a very interesting algebra. Actually, it corresponds to rotations. It represents rotations, but in 3D. In 3D, 3 dimensions. Rotations in our 3 dimensions. And some generalization of this is called biquaternion. It corresponds to our space-time, 4 dimensions. 4 dimensions. So it's a very, very useful thing. It's used in modern physics very often, and corresponds to the equations of movement of particles, quantums, and everything. Okay, this is just some a little weird but very useful example. So it would be nice if you remember something about it. Or maybe we will talk about it later at some time. Now 3 questions.
No, Tita. Thank you, Tita.
No, 3 questions, guys. Thank you. I know. The first question is, how many elements and what are the group which represent a rotation group with 3 elements? I'm sorry about elements. So 3 elements rotation group. What kind of degree is it? What is it? Just talk about this, think about it, okay? 3 elements. Remember, we talk about 4 elements, 2 elements, and 1 element, right? Now, let's talk about 3 elements, or the order of 3. Officially, order of 3 for this group. Order is the number of the elements. Second question is, try to calculate that kind of thing. 1 minus E multiplied by 1 plus E.
I mean, that's I.
I? No, this is question mark.
And what is, no, right, it's not E, it's I. What is...
I. I'm sorry, yes, I. And
what is I? The imaginary number?
Yeah. We talk about it, right away.
I wasn't sure. Okay.
Okay. And the second is just calculate this. Just to train a little with these things. How they just to get a touch on this and this. Calculate this and calculate this. Or simplify it, whatever. Simplify simplify this thing.
Yeah.
Okay? Okay. You got it? Okay, you wrote it?
It's something like 1 minus I.
Any questions?
1 plus 1.
Oh. Okay, just a second. I'll turn off the thing.
Okay.
Okay. See you next time, guys.